To work out the force between 2-point charges, we can use Coulomb's law. Coulomb's law is very similar to Newton's law of gravitation, but instead of having masses at the top, we have charge at the top. And instead of having capital G as a constant, we have 1 over 4 pi epsilon naught as multiplying the numbers. So epsilon naught is the permittive free space, it's a constant, and we can join it with the 4 pi to make this constant k. So this equation can be written as F equals k q1 q2 over r squared. And because electric field strength is defined as force per unit charge, we can divide it by one of the charges to get the equation for the electric field strength at the bottom, which can be written as E equals kq over r squared. Calculate the force between a proton and electron separated by a distance of 0.1 nanometers. So we'll have to use Coulomb's law. Force equals, firstly, the constant 9 times 10 to the 9, which is the constant, times the charge of a proton, 1.6 times 10 to the minus 19, the charge of an electron, 1.6 times 10 to the power of minus 19. Of course, there's going to be an attractive force because they're this opposite charges, divided by the distance between them squared, 0.1 times 10 to the minus 9 squared. This should give us 2.3 times 10 to the minus 8 newtons. Okay, what is the electric field strength at a distance of 3 times 10 to the minus 10 meters from a carbon nucleus? So we'll use E, the equation for the electric field strength. The constant, of course, 9 times 10 to 9, then multiplied by the charge of the carbon nucleus. Inside the carbon nucleus there are 6 protons, so it's 6 times 1.6 times 10 to the power minus 19 over the distance squared. This gives us an electric field strength of 9.6 times 10 to the 10 newtons per coulomb. So any charge placed at this point will experience that much electric field strength.